So let me start with some motivation introduction. In the last few years, we have seen really dramatic progress in the exact computation of supersymmetric partition functions in curved spaces. And while in some special geometries that contain a circle times an arbitrary manifold, the partition has a standard Hilbert space interpretation as a sum over states in the usual way, one can wonder what is the physical interpretation of the partition function of a conformal or superconformal field theory, say on a sphere. Okay? So the thing that I will try to describe today is what are two related questions. It's what are the ambiguities that the partition function of a conformal field theory on a sphere has, and what is the physical interpretation, if it has one, of conformal field theories. Okay? And then what we will use is is there a way of making this laser work?
Microphone?
No, the laser.
Oh, you have to hold it down.
Okay. And then what we will use is the physics, the formulas for the partition function of conformal field theories on spheres to give a microscopic description of how M2 branes can end on M5 branes to give you a surface operator in gauge theories. Okay. So let's start with something very simple. We're interested in computing the partition function of a conformal field theory. Generically, these conformal field theories can come in a family of conformal field theories that are parametrized, that are obtained by deforming the conformal field theory by an exactly marginal operator, where the couplings here lambda are the coordinates on the conformal manifold that defines the space of conformal field theories, and the exactly marginal operators are the vector fields in the conformal manifold. On this conformal manifold, you can define a canonical Riemannian metric that's obtained from the two-point function of the exactly marginal operators in this way. Okay? And this metric is a function on this conformal manifold. Okay? In this talk, I'll be interested in placing a conformal field theory on a sphere. At any given point in the conformal manifold, this can be done canonically by a stereographic projection. And the reason this is interesting is that this gives you a nice infrared finite observable that you can study. And since this partition function will depend on which point on the conformal manifold you are, it will give you an interesting probe of the conformal manifold of a given conformal field theory. Now, if you want to compute an observable O in the conformal field theory at any given point in the conformal manifold, one way of defining this observable is just defined as an expansion of this observable as you bring down powers of the exactly marginal deformations. Okay? Now, even though the original conformal field theory at a given point is completely well defined and you know the correlation functions at arbitrarily separated points, when you compute an observable moving in the conformal manifold, you will have to deal with these integrated correlation functions that give rise to ultraviolet divergences, where you have points colliding in the integration. So what we have to do is to renormalize this correlation function as you move in the conformal manifold so that the observables have a continuum limit. Okay? So let's do something very simple. Let's just study now, do some dimensional analysis and study the structure of divergences, ultraviolet divergences that the sphere partition function of a conformal field theory can have in even and odd dimensions. There is a very important difference between even and odd dimensions. So in even dimensions, you get power law divergences that depend on the cutoff with even powers of the cutoff. Then you have the famous logarithmic divergence, and you can have a finite piece. While in odd dimensions, you can have power law divergences that depend on the cutoff with odd powers of the cutoff, and then there is famously not a log, but you can have a finite contribution. Okay? So in order to give a finite observable, we have to renormalize the partition function in some particular way. And now what I want to describe a little bit is how do you parameterize the choices in the normalization that you have. And the very convenient way of doing it is to think of the choices of normalization schemes as local functionals of dimension smaller than the space-time dimension that you can construct from the background fields that your theory is coupled to, namely the metric. And it's always useful when you think in this language to think of the coordinates that parameterize the conformal manifold as background values for a field phi. Okay? So the ambiguities are parameterized by local functionals of the metric and this field lambda that have dimension less than d. Okay? Now, as you can expect, you can construct local functionals to remove all the power law divergences, both in even and odd dimensions. So now what remains is in even dimensions, the logarithmic divergence and the finite piece. Okay? So let's deal with them one at a time. So the first statement I want to make is that in even dimensions, the finite piece of the partition function is completely ambiguous because you can define a finite counter term. This is a marginal counter term, where E to n is the Euler density on the manifold, such that this quantity, if you integrate it over the sphere, it gives you a finite. So that means that the existence of these counter terms tells you that you can arbitrarily shift the partition function, the finite part of the partition function, by an arbitrary function f of 2n. And therefore, the finite piece is completely ambiguous and redundant. The other second statement I want to make is that there is no local counter term for the logarithmic divergence. That's a well-known fact. And furthermore, another important fact is that the coefficient of the logarithmic divergence is in fact independent of the point in the conformal manifold. And this just follows from imposing the West luminosity conditions. And then the coefficient that you get is precisely the Euler anomaly, or sometimes known the A-type anomaly of the conformal field theory. Now, in odd dimensions, I already said that the power law dimensions can be subtracted using standard counter terms. And the important thing to say is that just because we're in odd dimensions, there is no finite counter term that you can construct for the real part of the finite piece of the partition function. And there is a small ambiguity in the imaginary part that has to do with the fact that you can have Chern-Simons terms, but those are imaginary. So the point is that the real part of the finite piece of the odd dimensional partition function is completely unambiguous. There is any choice of regularization will give you the same answer. And again, just like in the A anomaly in the even dimensional case, consistency requires that actually this function is actually independent of the point in the conformal manifold. Okay? So to summarize this part of the story, what we found is that out of the sphere partition functions of even and odd dimensional conformal field theories, there are only two pieces that are unambiguous and physical. One is the coefficient of the logarithmic divergence, which is the A anomaly, and the other one is the real part of the constant part of the partition function on an odd dimensional conformal field theory. Okay? And furthermore, these guys are constant along the conformal manifold. And it's important to point out that these two quantities have a beautiful physical meaning as the entanglement entropy across a d-2 surface in your conformal field theory. Okay? So they're not only unambiguous, they have a direct physical meaning as entanglement entropy across the spheres. So now this was a discussion about counter terms and the physical meaning of conformal field theories with no extra symmetries. Now let's imagine that we study CFTs that have extra symmetries, and in particular supersymmetry. And we want to consider regulating the divergences that the partition function will have in a supersymmetric way. This obviously reduces the space of counter terms that you can have, because now you have to consider counter terms that are consistent with supersymmetry. And the question is there any extra physical information that the partition function of supersymmetric conformal field theories can have? So the first thing we have to do is regulate the divergences in some supersymmetric way. And the way you're going to regulate them is by starting with the superconformal algebra of the conformal field theory you're interested in, and impose only a massive subalgebra of the superconformal algebra. By this I mean you only make explicit in your regularization those supercharges that close into the isometries of the sphere, we're on a d-dimensional sphere, and possibly you have R symmetries. Okay? Generally, of course, you cannot regulate in a conformal invariant way the partition function. So the best that you can do is regulate by using a massive, what we call a massive subalgebra of the superconformal algebra. And this, in fact, is the most general supersymmetry algebra that a supersymmetric field theory on a sphere can have, a massive theory can have. Okay? Using the same logic as before is that we promote all backgrounds into fields, and what we have to do now to classify counter terms is construct diffeomorphism but now supersymmetric invariant counter terms of dimension less than d. And this is precisely where supergravity comes in. So what we have to do is classify supergravity counter terms. These supergravity counter terms will tell you the ambiguities of the superconformal field theory partition function. Okay? The way these supergravity counter terms are constructed is first you have to identify the supergravity, the relevant supergravity that you should couple your conformal field theory to study these local counter terms. And a very efficient way of doing it is to realize the supersymmetric sphere background, which is as a supersymmetric background in a supergravity theory in the framework of Fis-2-Chern-Seiberg. So you have a supergravity theory that admits some supersymmetric backgrounds. You represent your sphere that you're interested to study your conformal field theory as a supersymmetric solution in some supergravity theory. And this supergravity theory will have a metric, the gravitino, possibly other fields, and importantly, auxiliary fields, which are crucial in order to realize spheres as supersymmetric backgrounds in supergravity. Okay? So that's the first step. You identify the supergravity multiplet where this theory is the supersymmetric background of, and then you represent your moduli, the coordinates in the conformal manifold, as the lowest component or the bottom component of a superfield in that supergravity. Okay? So now the slogan is that the supergravity counter terms that will give you the ambiguities in defining the partition function of the superconformal field theory are supergravity invariants that are constructed from the supergravity multiplet and from the matter multiplet that parameterizes the moduli of your superconformal field theory. So now let's see a couple of examples and try to extract the physical information, if any, that superconformal field theory partition functions can have when you study them on spheres. So let's study with theories that I like two-dimensional 2,2 superconformal field theories. These theories are very interesting for many reasons. One of them is that they give a worldsheet description of string theory and Calabi-Yau manifolds, which is still a very attractive scenario to study chiral gauge theories in a theory of quantum gravity. For such theories, it's known that the conformal manifold is the direct product of two manifolds, what I call SC and STC. This you can think in the Calabi-Yau language. These are the moduli space of complex structure or Keller structure of the Calabi-Yau. It's easy to show that there is, now we want to study the partition function of the two-sphere as we move in this conformal manifold. And there are essentially two ways of regulating the partition function on the two-sphere, inequivalent ways of regulating on the two-sphere. Essentially, there are two inequivalent n equals 2 massive subalgebras on the two-sphere, which we denote by these letters A and B. This supersymmetry algebra is just the symmetry algebra of the most general massive 2,2 theory on the two-sphere. Okay? And these two different symmetry algebras are related by a mirror automorphism of the original superconformal one. Since in order to define the theory, we have to specify a given regulator, this defines two different partition functions, which are called ZA and ZB, that you can compute and has been computed using supersymmetric localization. Okay. Now you can ask the interesting question of what is, if any, the physical content of these partition functions ZA and ZB. And a result from some time ago is the interesting result that these partition functions compute the exact Keller potential on the conformal manifold. So for ZA, you compute the exact Keller potential in the Keller moduli space, in the Calabi-Yau language, and ZB computes the Keller potential in the complex structure moduli space. And the reason that this identification is useful is that this is an object that any way you want to compute, both from a physical point of view and a mathematical point of view, and allows you to compute, for example, exactly all worldsheet incident corrections to the Keller potential. Okay? Sorry? Genus 0, of course. I'm talking about the two-sphere, so yes, Genus 0. Now, of course, the Keller potential, we all know that has a Keller ambiguity. So you can shift the Keller potential by a sum of a holomorphic and an anti-holomorphic function. We already see that in the context of supersymmetry, the space of ambiguities of the sphere partition function has been reduced from the bosonic case, where we had ambiguity by an arbitrary function of the moduli. Now the ambiguity is by an holomorphic function of the moduli. Okay? So now we want to understand how to think of these ambiguities from this supergravity local counterterm point of view. And the way you construct that is essentially by constructing a counterterm in the corresponding supergravity theory. So there are two supersymmetric two spheres, let's call it A and B. These are associated as supersymmetric backgrounds in two different theories. It's called supergravity A and supergravity B. Okay? Then you represent the coordinates in the two factors of the moduli space as bottom components of the relevant multiplets. In one case, it's chiral multiplets. The other one is called twisted chiral multiplets. And for example, for the case of the type 2B theory, you can construct in that supergravity an explicit supergravity coupling. It's an integral over half superspace of chiral superfield that contains the Ricci scalar as its top component, and an arbitrary holomorphic function of a chiral field whose bottom component is the coordinate in the relevant conformal manifold. When this coupling is evaluated on the supersymmetric two-sphere background, it gives you precisely the ambiguity by an arbitrary holomorphic function of the moduli. Okay? So this is a microscopic understanding of where the Keller ambiguity comes from the point of view of the two-sphere partition function. An analogous thing can be done to construct the local supergravity counterterm for the other theory that now will involve an integral not over the other essentially Lorentz invariant half superspace that you can construct in 2D n equals 2, 2. Okay, so now let's move on to something different. Now I want to ask the similar question. Now that we have understood that at least in 2 dimensions we can compute the exact Keller potential from these S2 partition functions, we want to go back to the case of 4-dimensional n equals 2 superconformal field theories and understand what does the partition function of this theory compute. Okay. The main point here is that, again, this superconformal field theory can have exactly marginal deformations that are parameterized by these operators Ci, which are the top component of a 4-dimensional equal chiral multiplet, which has bottom component Ai, and Ti are the coordinates in the conformal manifold. Okay? Again, the partition function of this superconformal field theory is ultraviolet divergence, and we regulate it using this massive subalgebra of the superconformal algebra. Now imagine, in order to extract what the physical content of this object is, imagine looking at this particular observable, the derivative of the log of the partition function with respect to the moduli. This essentially gives you the integrated 2-point function over the top components of the exactly marginal operators. Okay? Now what you can do is using either supersymmetric localization to compute this object exactly, or if you're lucky and strong enough using word identities, you can show that this integrated 2-point function can be reduced, can be localized to the 2-point function, an integrated 2-point function of the bottom component of the same chiral multiplet evaluated at the north and the south pole of the sphere. But then through usual standard word identities, this is essentially precisely the definition of the Zamolodchikov metric that I gave in the first transparency. And therefore, that you arrive at the conclusion that up to Keller ambiguities, the partition function of the 4-dimensional equals 2 theory, once you put the right numbers in, computes the Keller potential on the conformal manifold of the superconformal field theory. Good. Notice that I omitted the case of the very interesting case of 4-dimensional n equals 1 superconformal field theories. I want to say what the story there. And essentially, since time is short, all that I will say here is that in this case, there is a local counter term, explicit local counter term that you can construct, which I just flashed here. I'm not going to explain what all those letters means, which essentially demonstrate that in this case of 4-dimensional equals 1 SCFTs, that you can shift the partition function by an arbitrary function, real function, of the moduli, and therefore the finite piece of the n equals 1 SCFT partition function is completely ambiguous, just like the bosonic case, just like for the standard CFTs. Okay, so what we've seen, essentially, the point that I want to mention is that we found that the sphere partition functions of 2D n equals 2, 2 and 4D n equals 2 superconformal field theories compute the exact Keller potential on their conformal manifold. And now what I will do is use these powerful results to give new insights on the microscopic description of M2 branes ending on M5 branes. So let's start. This is some work that should appear soon with Bruno Leflo, my student, and he's applying next year, so don't forget his name. So this describes, I want to describe the following brane configuration. So you consider M5 branes intersecting with M2 branes along a surface. This defines the surface operator in a 6-dimensional 2,0 theory that lives on the collection of M5 branes. These surface operators are believed to be labeled by a representation R of SU and F, where an F is the number of M5 branes. If we now consider, it's well known that it's been very popular that if you consider these M5 branes, instead of being in flat space, you put them on a Riemann surface, in this Partition Riemann surface in this direction. This gives you a very interesting way of generating 4-dimensional n equals 2 gauge theories. Okay? If we now enrich the M5 brane with this M2 brane intersecting along a surface, what this object does is define or insert a surface operator in the 4-dimensional n equals 2 gauge theory. And now what I want to give you is a microscopic description of how to construct this for this surface operator for an arbitrary M2 brane ending. Okay? So just these are a couple of slogans about what surface operators do. So these are new order parameters that go beyond the usual Wilson-Latuft order parameters of gauge theories. The thing that will be important for me is that these operators can be defined. One way of defining them is by adding new degrees of freedom on the surface where there is the intersection and coupling those two, localized degrees of freedom to the bulk theory. Integrating them out give rise to a singularity that is the singularity of the surface operator. And the thing that's interesting is that if you think of the surface operator from this point of view of coupling a 2D degrees of freedom to 4D degrees of freedom, the combined system can exhibit new dynamics and dualities that go beyond the dynamics and dualities the 4D theory or the 2D theory can exhibit separately. Okay. In this context of M2 branes ending on a collection of M5 branes wrapping a punctured Riemann surface that generate realized 4-dimensional equals 2 theories, the supersymmetry preserved by this M2 brane configuration is precisely the 2,2 two-dimensional subalgebra of the original 4D n equals 2 supersymmetry algebra of the 4D n equals 2 theory. And this precisely puts together the two stars in the first part of the talk, the 4D n equals 2 theories and the 2D n equals 2,2 theories. So now the main claim, or one of the main claims in our paper, is that we have identified which two-dimensional gauge theory corresponds to any of the M2 brane configurations that can end on the collection of M5 branes. So as I said before, this collection of M2 branes endings are labeled by a representation of SU and F. This can be conveniently parameterized by a Young diagram with boxes n1 minus n2 in the first column, n2 minus n3 in the same column, and so on. So this describes a particular representation of SU and F and corresponds to a particular ending of n2 branes on n5 branes. And now the claim that the identification that we have is that the insertion of this surface operator of the M2 brane ending can be represented by coupling to your 4D theory to this very specific two-dimensional n equals 2,2 quiver gauge theory. So there is a quiver gauge theory. I don't have time to explain the notation. I think it's pretty standard. With the information about the representation of SUN encoded into the gauge groups here. Okay. One thing that you have to do is you have to construct a surface operator. Now you have to couple this theory to the bulk 4-dimensional theory. And the way you do it quickly is that you identify the obvious SUNF times SUNF times U1 global symmetry that you have on this node with the 4-dimensional SUNF times SUNF times U1 flavor or global symmetry of the 4-dimensional theory. So this in pictorially, this can be represented by a kind of a quiver diagram. This would describe the coupling of a 4D theory, which is super QCD, conformal super QCD, SUNF coupled to 2NF hypermultiplets. The way you define the surface operator is by weakly gauging these symmetries and attaching it to these nodes in this way. Okay? And this can be represented by a two-dimensional superpotential. Okay. So it was a flavor from the point of view of the 2D theory, but it's a gauge group from the point of view of the 4D theory. It's kind of a cookie notation that Brun invented. Now let me go back. So how can we test this idea? So one way we can is that it's known from the work of AGT that the four-sphere partition function of the 4-dimensional theory that wraps this punctured Riemann surface can be given by a total CFT correlator on the punctured Riemann surface. Okay. Short after this, it was conjectured that adding a degenerate puncture to this Riemann surface corresponds to inserting some surface operator, but there was no idea what this surface operator could be. So what we now explicitly propose and check is that if you take the partition function of the 4-dimensional equals 2 theory TC associated to the Riemann surface C, and you couple a two-dimensional gauge theory which is labeled by the representation R of omega, omega is the highest weight of the representation R, that this is captured, the partition function of this combined 2D 4D system is captured by the total CFT correlator on the same Riemann surface where you added an extra degenerate puncture corresponding to the degenerate field with momentum minus B omega, where omega is the highest weight of the representation. Okay? That's the proposal. And what we've done using the working horse here was the exact result of the S2 partition function of two-dimensional n equals 2,2 series. What we have done is explicitly verified that the partition function for an arbitrary representation and for the three-puncture sphere, for the theory, the 4-dimensional theory that defines the three-puncture sphere, that the partition function of the combined system for an arbitrary surface operator is given precisely by a total CFT correlation function with a very specific degenerate insertion. Okay. The last thing, I'm probably running out of time. Yeah, so let me just say very quickly that the fact that we can represent two-dimensional gauge theories as total CFT correlators gives you a very elegant way of representing dualities, two-dimensional dualities as symmetries of total conformal field theory. Let me just flash two simple examples. You can construct in 2 dimensions two-dimensional analogs of Seiberg and Kutazow-Schumer dualities. And these have a very simple interpretation from the point of view of the corresponding to the CFT correlator as just trivial charge conjugation of the total CFT, where you conjugate all the moment of your vertex operators in some way. Or you can define Seiberg duality or two-to-star dualities for quivers by essentially taking two degenerate punctures. So this dotted line corresponds to the degenerate punctures that you added to your theory, and just braiding them. This gives you the Seiberg dual or the two-to-star dual theory. So here I was describing just what the dual theories would look like. That doesn't matter too much. Let me just conclude very quickly. So in non-supersymmetric conformal field theories, what we found is that the real part of the finite piece and the anomaly coefficient are the only scheme-independent parts of the partition functions, that the sphere partition functions of 2D n equals 2,2 and 4D n equals 2 capture the exact Keller potential in the conformal manifold. We gave an explicit supergravity microscopic realization of the Keller ambiguities that you expect given the identification, given a microscopic description of all M2 brain surface operators, and we have realized dualities in two theories as just elementary symmetries of total CFT. And with that, I'll stop. Thank you.